So I'm going to present a work with my PhD student, Thaïs Baudon and Laure Gonnord. And so this is a sort of follow-up work of something that was presented last year at ICFP, which is the quest toward custom memory representation for algebraic data types. And so, okay, a quick sort of recap. So we have lots of algebraic data types. So here is an example of one. So this talk is going to be in a Rust-like syntax. Why not? So here we have an enum color, which is either red or black with two constructors. And when we have an algebraic data type, RBT for red-black tree, which is either a node with 4 fields or empty. And we have an example of a value on the right. And the nice thing about algebraic data types is that, well, we can write pattern matching. And so we have this cardinal function here, which is simply a case analysis. Either it's empty and it's 0, or it's node and we can count the subterms. And with some nice typing, we can check for lots of properties, including, for instance, exhaustivity, non-redundancy, and so on and so forth. This is very nice. Now, what happens in the real world? Oh, okay, no, before that, another thing that is pretty nice is that we have access to lots of tools, and so we can write complex pattern matching in a pretty compact way. So this is a balance operation on red-black trees. It's a bit of a mess, because the operation is complicated, but it expresses exactly what we want, and the exhaustivity and non-redundancy are going to check that we are doing a good job. Okay, all right. Now, what's going to happen in a traditional language is that we're going to have a memory layout for our representation. So here is an example of a fairly naive memory layout for red-black trees. A node is going to be a pointer over 64 bits. And then we have 4 fields, and so we will have a header, probably in most languages, and 4 fields. The black is a 2-value, but here it's very naive, so it's going to be represented on 64 bits. And at the end we have an empty, which is a null pointer in practice. Okay, good, excellent. Now the problem is that in many performance-intensive representation or performance-intensive code, they do not want representation like that at all. So there are red-black trees in the Linux kernel, and they are represented like this. You have a node, which is a pointer, and then they have a parent pointer, so a pointer to the parent of the node, where they use one of the bits to encode the color, because this pointer is aligned, so the first bit is always 0, so they can hide something here. Then you have a first child, the second child, and the value. And now you have a much more compact representation. You have an additional pointer, and so on and so forth. So you've seen, for those who've seen the paper on double-ended bit stealing, you can see how far we can go with this kind of representation. So if you look at the Linux kernel code, you can see this kind of code, which is basically a mess of pointer shuffling to figure out exactly where to put things. So for example, here we have a code which is half a case of the rebalancing operation, and which is already a page long. So our contribution is a custom memory layout for algebraic data types, we will have an input language where we can specify exactly the layout of the memory representation, and we will check that it is indeed a good representation for the algebraic data type. And then we have a bunch of compilation algorithms for pattern matching and for data constructor and accessor, and this is a new bit compared to the last paper. If you want to play with it, you can go to this link here, where you will have an online demo with example where you can play with the code. And it will show you lots of graphs. Okay. So I will go progressively. I will start with the high-level type and the for the algebraic data types, and how to express memory layout for an algebraic data type. So let's go back to red-black trees. We're going to try to build with Ribbit Linux-like red-black tree representation. So this is going to be our representation for this talk. We have a color. It's going to be on 1 bit only. Red is 0, black is 1. And then a red-black tree is going to be either empty, which is going to be a word of 64 bits, where 1, the lowest bit, is 1. And we don't care about the rest. It can be whatever. And then the node is going to be a pointer to 3 fields, which are the value, the left, and the right trees. And then the color is going to be sneaked in one of the lowest bit of the pointer. And then we're going to keep 0 at the lowest bit. So that's our representation. So you notice we don't put the parent pointer that was there in the Linux representation. That's just because our small language is pure, and cyclic pointer in a pure language are annoying. So it's not a real limitation, it's just we didn't do it in the small prototype. All right. So, any question at this point? Okay, let's go. Now, for each type, we will have a high-level type and a memory type. And so, for example, for the red-black, for the color, we'll say represented as to express the low-level type. And the first construct we have for low-level type is what we call a split. A split expresses the fact that we have several choices. Here we have a split that says that the memory representation depends on the current value, the value that we have at the root right now. And if it's a 0, we say it comes from the red constructor, and we sort of repeat the fact that it's 0 on 1 bit. And it comes from 1, it is 1 on 1 bit. So here we have various pieces. We have a discriminant value on the split that say how we are going to differentiate the various cases of the representation. And we have what we call a provenance that says, okay, this case, this particular representation is there because of this constructor. So here I am in this case because this was a red value. And so this is shown graphically on the right. Either it is red, black, 0 on 1 bit, or 1 on 1 bit. Okay, so we have a simple enum. So obviously, like, if it was just an enum, we wouldn't need anything like that. This is a bit over-engineered for the representation here. So we could just express that directly. But it's going to be more useful when we move to bigger representation.
Sorry, if I look at this and I would just specify this,
Mm-hmm.
then what would your code generator do if I just have one enum color value? How is that going to go into memory?
What do you mean?
I think this is meant to specify how this is being mapped into memory.
Yes.
But so this specification is yet incomplete, right? You just
So you're right. So you can have yes. So you can. So far in Ribbit we sort of don't really mind that part as well. You could have in your language a compiler deciding that everything that is smaller than 64-bit is going to get put in a word. The reason we have 1 bit here is for composition. If it's going to be put in something else, then it's going to be 1 bit, and that's the goal. But yes, if this value is unboxed in a computation, then you need additional rule on top of that.
Sorry, it is redundant because since you have 2 constructors, you can easily understand that you need just 1 bit, right?
Yes.
If you have 3, you need log.
Yes.
Stealing of log 5.
Yeah. We're going to, and we're checking for that.
So why do you need to specify this?
Because I want to introduce split to you, and this is the simplest example ever. But yeah, as I was saying, this is really over-engineer for enums, definitely. And so, like in practice, in Ribbit, we have something that's going to say, please generate this for me, and I just do the thing, and it will work. Yes. All right, so now let's move on to a more interesting type. So again, we have an alternative. We have either an empty or a node. But this time you notice that the way I'm going to distinguish an empty from a node is by looking at the lowest bit of the word. And so it's not just the whole word I'm going to look at because, well, there is a pointer, so I don't really want to look at that. But I'm only going to look at the lowest bit. And so I'm again using a split. But this time the location say, please look at the lowest bit of the current value. So I have my split, and then I need to do the various pieces. So at the lowest value, at the lowest bit, I have either 1 or 0. I mean, it's a single bit, so anyway. I can give the provenance, either it is empty or it is a node. So now let's look at the empty case. The empty case is pretty easy. We don't care. Like, it can be whatever, because there is nothing of interest in the empty case. And so we just have a wildcard that's going to be on 64 bits. And just for consistency, we sort of repeat ourselves with what we called a bit word specification. Let's say, in this last bit, so the range here, please put a 1. So again, this is the whole purpose of example. In practice, Ribbit infers that part. You don't really need to repeat yourself. But here, for the purpose of the talk, we will be very explicit. Okay, so the empty is any word of 64-bit whose last bit is 1. Excellent. Okay. Now, in the node case, I told you the node is a pointer to 3 fields. And so this is a pointer here. And we're going to have a bunch of stuff as a pointee. But first, we have to specify what are the lowest bit of the pointer, because we're going to steal the lowest bit. And so one of them is going to be a 0, again, here. And the 1 here is going to be the color. And so here we have to point out the fact that, okay, the color, which is at this point in the original value, is going to be placed here. So we call that a fragment. It's a fragment of the bigger type. And we are going to verify that, this color is on 1 bit. It does fit inside this place. And it will work okay. Okay, and then we have the content of the pointer to look at, and it's going to work exactly like a struct. And so we are going to have several fields, 1, 2, 3, that correspond to the value, the left-hand side of the tree, and the right-hand side of the tree. So we are going to have 3 fragments to represent that. I have lots of time, so I can take questions during the talk, if you have questions at this point.
Sorry, everything is not boxed in this talk, right?
Yes. I mean, boxing is explicit. You will put a pointer. So, yes.
Why do you need to specify the types of everything?
Haha. Good question. It's not the type, it's a representation. It just happens to be the same name because we only have one representation for the types in this talk. But you could give another representation, and you can have several representations for the same type.
Will we see polymorphism later?
No. Okay. Sorry.
Are the memory representations kind of separate? Are they always used like homogeneously? Or can I have one representation that has as like sub-representation of the recursive parts with another one? Is there any use for this kind of thing?
Yes, it's later in the talk.
Oh.
You can be as non-uniform as you like. You can do whatever. You can inline two level of trees if you want in one node and make a big flat node. You can shuffle around the fields. You can, go banana. Like, it will work. And we actually have a proof that it works. Well, it's not in the paper, but it's in Thaïs thesis. Right. Okay. So now we have a full representation. Cool. What can we do with it? So we can verify that it actually works. So we have formal criterions that are going to assert that this is indeed a good representation. And so there are several of them. I'm going to highlight 2 of them. One of them is distinguishability, which means that, we have encoded some type. The primary purpose of some type is pattern matching on them. And so we should be able to distinguish, based on the representation, the various cases of the sum type. And so here it's pretty easy. We have only one split to look at. But you could have various species in the value that indicate one case or another, and it could be a compounded information. That would work as well. Another thing is coverage. We have encoded a value. We need to find all the pieces of this value. Otherwise, it's not a good encoding. And so here, by color, it's correct, but there is an actual formal version of that. Here we have both cases, and we have all 4 fields of the node case that are in the value.
Now, they give the full power to the programmer.
Mm-hmm.
The question is, can you specify these descriptions in a hardware-specific way? For example, I may have an architecture that does not support 64-bit pointer but 32-bit pointer. I may have an architecture that doesn't take it lightly if you mess around with the lowest 2 bits because they have implemented some weird stuff on the architecture.
Yeah.
And you need to have an alternative representation. Can you do this?
So far in Ribbit, we haven't done it in the prototype. There is no reason we cannot, because, I gave you a notion of pointer here. I can give you another notion of pointer. The pointer are size dependent, so you can change the notion of pointer. You could also decide, okay, my pointer, you do not have the right to mess with the higher bits, for instance, if that's forbidden in your case, and so on. So
the question is, can you check this?
yeah, yes, it will not change much about the checking of the validity. But no, we haven't implemented mostly because it's a question of how do you present this diversity to the user, and I do not have an answer to that. Like, it is a very complicated amount of things to present to the user, especially if you start talking about embedded, where like everything is weird. And so I don't have a good answer to that aspect.
Just want to confirm those are all curly braces.
Yes.
What does that mean?
Those ones?
Yes.
It's a struct.
It's a stuff.
It's just a struct. It's like several fields unboxed in a piece of memory. And that's it.
But it appears to be an address, a reference.
The pointer is outside. So there is an explicit pointer to a struct. But yeah, if we go back, the struct, the double bracket represents this part here.
I just want to have, we only have 6 full bit left for this word.
No, I'm not sure I understand the question.
So the whole word is 6 full bits?
That's the size of the pointer.
Yes.
The size of the struct is deduced by the size of the content. All right. Okay, now, so this, so if you were here last year for the previous talk, there is nothing new here. It was all there previously. Now I'm going to show you another example of representation, which might be slightly surprising in a way, is that let's look for a moment at the RISC-V instruction set assembly. So if we look at RISC-V instruction set assembly, here is a representation of the store word instruction, and it has, in the assembly, it has 3 parameters, x0, x1, 42. So it's the address of the word, the address of the content, and the offset. And it's going to be represented like this. The x0 is put somewhere in the middle. The x1 is put somewhere here, so before the other argument. The fact that it's a store word instruction is split into 2 parts. 1 bit is here and 1 bit is here. So we have 2 pieces. And the offset is also split into 2 parts. 5 bit at the sort of beginning and 5 bit at the end. So you've seen like this representation is a bit weird. We've split various places with our constructor, the store word, is also split into 2 pieces, and so on and so forth. And so the new thing is that nowadays we can actually represent this kind of thing exactly as a layout of an algebraic data type. So let's look line by line. At the beginning we have the name of the register for RISC-V, so they're x0 to x31. And as I said before, we can explicit that representation, but we can just ask Ribbit to do it for us, and I just ask, okay, please give me exactly the representation of C, and it will do that for us. And then I have the representation of a 32-bit instruction in RISC-V. And so it's just a constructor with some register and a 12-bit integer, and then I can have other things. And then I can fully write exactly with all the ingredients that I gave you in the previous example, this representation. And so if I took a concrete piece, for example, from the bit from 7 to 5, so this corresponds to this piece here, I'm going to have the second field of the SW instruction, and I'm going to take the bits from 0 to 5 as a 5-bit integer and put them at that position. So it's very tedious to write, but you can write everything pretty precisely, and it will exactly have the expressivity that you need to encode this kind of splitting of various species.
Sorry, but when you write I5 is signed integer or unsigned?
In this case, it's unsigned, because in the representation there is no notion of signedness.
So it's all over.
Yeah.
And you have regulated all over the...
In this case, yes. It is sort of related to Sven's question. We could have both. Making it parametric would be difficult, and again, I do not know how to expose that to the user.
With the code that you were showing, it looks like we are only looking at the 7 moments for the constructors.
You are right.
And completely ignoring the ribbits.
Yes, that's because it's slightly too simplified for the slides. You can have a split inside a split. So you can have, you can even have multiple arguments in a split. Like you can say, I'm going to split on this position and this position and do list all the values. So yes, yeah, it's simplified a little bit for the slide. We do specify that there is a constant, the right constant here and here. Yes. But yeah. Okay. And so now I'm going to. So we have a type that is pretty nice. We can do this weird type with lots of pieces. Now I want to compile code. So here is an example of code that uses the RISC-V instruction. It basically tests if something is compressible or not. So 32-bit instruction RISC-V can be compressed to 60-bit instructions, some of them, not all of them. And so here it looks at my assembly language and it decides, can it be compressed or can it be not compressed? And so in my input language, I'm going to have various ingredients. The green part is the pattern matching aspect. So I'm going to have to compile my pattern matching so that it works. The blue bits are, I'm going to take pieces inside the representation, and so I have to be able to extract those pieces and use them. And the teal, I don't know what's the color in English, this color represent constructors, which means that I have to be able to construct values, of course. And so there is one more complicated at the very beginning. So this is the big piece I will have to compile. And so let's try to give you a hint of how it compiles. Any question at this point before I move on?
Yeah, so this is a small one. If you have multiple, you said you could have multiple representations all at the same time?
Yes.
So you would have to do all the possible
Yes.
combinations?
Yes, we can do that. Here, in this specific case, implicitly you're choosing one here.
Oh, okay.
Yeah. We don't specialize the code. You just give us one, and we do it.
So when you write code, you have to say this is a function that applies on this specific representation?
In our prototype DSL, yes. In a real language, I don't know what's the best solution for that. I think it depends a lot on the language. Okay. So I have expressed my memory type. I have associated my nice high-level data type with a memory type, and now I need to do my compilation. And so, as you've seen here, the code is completely standard ML-like code with constructor. With algebraic data type. There is nothing special in the code whatsoever. All right, so let's first go quickly over the pattern matching. So pattern matching, if we look only at the pattern matching, it looks like this. You have a bunch of cases and maybe some nested constructor. And so for this, we're going to output a layout-specific decision tree that's going to look directly inside the representation to the specific bits. And so if you want the details for that, you can look at the paper from ICFP last year. I'm not going to go into much detail on that. But yeah, we can output the decision tree that does everything for us. You notice that in this pattern, I remove all the binders. That's not by accident. The decision tree is only going to tell us in which case we are, but it's not going to extract the values for us. So we need to do more work. So before we do more work, we're going to move to a slightly nicer intermediate representation. We start with this. This is the same code from before. And we're going to move to something like this, where all the binders are extracted and moved to the code as accessor. And so if we look at a specific accessor here, we have x, which is the original value, in the SW case, and we access the zeros field. It would not be a nice surface language, but for an intermediate representation, we are guaranteed that we are indeed in the SW case, so this is fine. Now, let's look a little bit how we might compile this kind of code and the work we have to do. So if we are looking at an instruction, a particular instruction, so this one here, and I call isCompressible on it, first I will match. And when I match, I will look at the two places in my type that I have marked as criterion to distinguish values in my memory representation. And that gives us which case we are looking at. And here we are looking at SW. And then I have to extract various bits. So if I want to test this expression. And so I have an accessor x SW0. It's coded at one thing here. So I can access it directly. This is easy. Same thing on the other side, x.the_sw.1. This is this bit here. I can access it directly. And so I just need to do an access inside my word and do as the appropriate mask. Okay, excellent. Here the constructor are simple integer, and I can find the right integer and do that. Okay, so this is still pretty straightforward. And finally, here I have another test which look at the value of the offset of star word. And in this case, this is split over 2 bits. Now there is the 5 bits at the beginning and the 7 bits at the end. And so I have to fetch both, glue them together, create a new value that I can then use. And so on integers, this is pretty easy. In practice, this can happen over arbitrary representation. So I can have an arbitrary representation on one side, another arbitrary representation on one side, combine them, and then expose a value. And so what we sort of realize is that basically we have to combine arbitrary morphism from one representation that reorder everything inside to another representation. And this is necessary to compile this. And so we have an algorithm that synthesizes the code for this kind of arbitrary transformation over representations. And so the compilation algorithm, I'm not going to show you. It's in the paper, and you can look on the link on the ICFP website. It's a bit too complicated to fit into a few slides. But the key idea is we're going to go back and forth between 2 states. One state is I am building something in memory of a given shape, and I know this shape because I have the memory type. And so I will try to build all the structure, allocate the stuff in memory, and so on and so forth. And then at some point there is some bit that it's not known, and so I need to go look for it. And so I'm going to move to a second state. I am looking for something in memory of a given shape. And then I'm going to look inside the various pieces that I have, my different binders and all that, find the pieces and put them at the right position. And so we emit code in destination passing style. You saw destination passing style in the previous slide, conveniently. And we emit code with explicit casts and allocation on the different memory representation. So for the example, it looks like this. You don't have to read it. The important bit is that the bit in purple here is the pattern matching stuff. And here in green is the SW case, which gives a pretty compact code in practice. All right, I'm going to stop here. I think this is enough talking. So we have an expressive DSL for custom memory representation. It can capture lots of weird representation. We can encode what I showed you on RISC-V instruction, on NAND boxing, and so on and so forth. We had to invent new compilation algorithm for this. In practice, they are pretty powerful. They can do arbitrary transformation on memory layout. For instance, if you have a given type and you give two memory layouts, we can synthesize any transformation between the two. We have a formal semantics and formal agreement, and all the compilation algorithms are proven correct, either in the paper or in Thaïs thesis. So Thaïs is defending next month. So if you're interested in this kind of stuff, you can look at the manuscript as well. And that's it. I will leave you on a final funny representation, and I will take questions.
Thank you very much. I am going to. What is the target of your compilation?
Okay, good question. So we used to target LLVM-IR, and by doing this last bit of work, we realized LLVM-IR is too high level for us. It doesn't give us the right casts. We can do cast on memory representations that LLVM does not agree with because we have more type information. And so right now it's custom. We would like to go back to LLVM-IR shortly. But right now it's just, we have a custom target and interpreter for that target.
It looks like from this presentation that this language is good potentially for the description of the decoder CPUs. So I'm planning to target system Verilog. Verilog for PGAs, because there will be a problem with timing, of course. So you cannot assemble combinatorial logics, which is very
we could do that. Well, okay. It's probably a good idea to do that. Personally, I have no expertise whatsoever in doing hardware emission. I'm very wary of the timing issues and all that, and I must admit I don't know much about it. So I'm not planning to investigate that in the immediate time. But yes, you're not the first one proposing this. Yes.
The future benefits seem to be very, very high, right?
Mm-hmm.
The benefits seem to be big, large.
Yes, I hope so.
You can see this pattern matching and understand.
Yes. So, I mean, it's a very low level, so it should work well at that level, at the hardware level. But yeah, as I said, I don't know well. I don't know much about it, so.
Have you tried to use this in the
you try to use this in the context of Linux kernel codes to verify the Linux kernel codes that use different representations. Because I would assume if this has been hand optimized, and yes, they have a library that they trust, but it would be nicer if you have kind of a verified code generator, right?
Yeah.
So they could write an abstract algorithm, have a Ribbit specification, and get the highly optimized version out of it. Is that an avenue that you have looked into?
Not really. One of the reasons for that, I mean, this is definitely designed to be inside a programming language. If you want a verified toolchain, D'Argent does that very well. It does exactly what you would suggest. You write code, you specify some memory representation, which are slightly less complicated than that in many ways, but more interesting in other ways. It's not exactly the same expressivity. And then it emits C. And so, yeah, D'Argent does that very well. So I think Ilya Sergey also has a thing where it does a verified compilation of C to C. So yes, this is like, maybe you can do it with that, but this is definitely designed to be inside the programming language, which means that we don't try to go too far with, for example, size constraints or this kind of thing, checking that this field is exactly the size that you expect, or this kind of thing. We don't try to go too far because we want to be, we want everything to be decidable. But if you drop that part, then you can go the D'Argent route and discharge to a solver and or a solver or a proof assistant and emit verified code. So.
No, I was not trying to go that far. The idea was just more to say, okay, if I have a specification in C that is more high level, and then I have my records there, and I have my types, and I write the algorithm like a textbook algorithm, and I'm kind of happy with it. Yeah. And then somebody comes along and says, "Ooh, but we have a performance problem here. You have to map these into this structure." Yeah.
So we can do that. Yeah. Yeah.
Do you have a system for that where I can have a C program, say, and then I add a Ribbit specification on how to map the data structures into memory, and then I press a button and out comes a refactored C code?
So I would like to have a C output at some point, which would, I guess, help with that. Yeah, I would love to. My ultimate goal would be to put that into Rust, and then you would have that as well. Yeah.
Do you have like a nice way of representing all these memory information? Did you look or think about how to kind of automate, like, oh, I have a data type and maybe have some code that does stuff, and I would like to find the best memory representation for some definition of best for this code or this data structure?
Yes, so this is an University project. So yes, I would like to do that. Do you have 3 PhD students worth of funding to give me? No, my idea is twofold on that area. First, we could do a pretty decent job at doing it piecewise, like for example, looking at the algebraic data type and trying to generate a memory type that is decent, for some definition of decent. The difficulty is that it's a very complex set of trade-offs between, size, indirections, sharing, preserving sharing or not preserving sharing, these kind of things. So complicated trade-offs, so difficult to automate. The second route is doing what you do in Gibbon and local, which is to do a whole program analysis to figure out the right representation. So far, I'm not fond of doing that because I will never be able to put that in Rust. So yeah, or in any kind of normal language. And the last solution would be to be profile guided. And I haven't tried. I think it would be amazing, but it's definitely at least a PhD, at least a full PhD to figure that out. So, yes.
So, is there a reason that polymorphism isn't supported?
It's yeah.
What's the particular reason?
There are lots of reasons. It's difficult to fit polymorphism in that. There is a simple notion. If you like put constraints such as every polymorphic type is boxed, it is a pointer of 64 bits, and whatever is underneath is whatever, you can add polymorphism. It will be fine. If you need polymorphism with unboxing across polymorphism, then you need a whole kinding system. So you end up with something that sort of what is in GHC really, and what is going to be eventually in OCaml if Joint Street wants to add it. So you get lots of complication. What we need to know is the size of the data. If we don't know the size of the data, then it doesn't work.
Yeah, so it's more of a, let's say, separate compilation versus whole compilation thing then.
Yeah.
Because, you need to preserve types across module boundaries to figure out.
Yeah, and of course there is another solution, which is the Rust solution or the C++ solution, which is to monomorphize everything first and,
so whole
and
program.
decide later. It's like a shoot later, ask question, shoot first, ask question later kind of approach, and then that would kind of work.
I just curious how is endiness a concern here, or do you assume certain endiness?
Sorry,
Endiness. Yeah, the ending of the architecture.
Yes.
The,
What's the question?
Do you assume certain endiness of the architecture, or?
So far we did it everything in the traditional way, so it's little Lydian, if I can never figure out which it was.
Intel's little. So
Yes, exactly. So we do everything in little, but it doesn't really matter to us really, as long as we know. So we could vary it. But again, going back to Zen's question, I don't know how to expose. I don't know how to make it parametric, and I don't know how to expose that to the user. So.
Would it be possible to have sort of a parameterized representation? So for example, I can represent any size of floating point number, and then I do like calculation with the parameter so that I ensure that the correct properties are always...
So we tried very hard in Ribbit not to have to do any kind of integer arithmetics.
Okay.
Because decidability. That's the main reason. Could we add a little bit and have a solver on all sides? Maybe. If it's only like linear constraints, then we could do it. But I expect if we put a little bit in it, people will want a lot more. Yeah. But the good thing is that so far we haven't needed to. We haven't really found a very good example where we would need that kind of power for what we do.
I imagine it would be kind of useful for example, doing machine learning with mixed precision operations, things like that. So you can use a single program representation to have like automatically converting between the different like specific representations with different sizes and always ensuring that they are equivalent.
I don't know. I would need to see the example. Yeah, I would need to see the case. But one thing I need to add is that we don't have arrays. When we have arrays, which is the next thing we want to add, then we might need a bit more arithmetics.
Okay.
All right.
Should we wrap?
I think so.